Hello, my name is Reide Corbett, and I'm going to talk to you today about short-lived radioisotopes, their principles primarily, and some of the laboratory techniques to get you some of those results. This is sort of a general overview, something I use to talk about how we can apply radioisotopes to understanding different processes across the environment. I generally use this to talk about the marine environment, but you can apply these different isotopes across many different environments, from wetlands and coastal systems to terrestrial systems, lakes, rivers, and of course across the marine system. And this is a product of using these long series uranium-238 and thorium series radionuclides that have many parents, granddaughters, daughters, to those radioisotopes that are falling out of the atmosphere. Some of those are man-made, like cesium-137 or plutonium-239, 240. Some of those are naturally created in the atmosphere, like C14 or beryllium-7, that come out of the atmosphere through both wet and dry fallout. And so what's important to understand is that the process that you're interested in understanding, you need to have an understanding of that time scale, and ultimately picking radionuclides that will work for that time scale, but also for the environment you're interested in, particle reactive, or you're interested in what's happening in the water column, those sorts of processes. It's important to understand the chemistry as well as the time scale at which these things are happening. The reason we can use radionuclides is because they are not stable, right? I mean, they are decaying through time. The idea that radionuclides are a clock, right? That they have a rate of change, a known rate of change, and that change rate is on an exponential decline. Knowing that and understanding sort of the physics associated with radioactive decay, we can then apply this clock to processes that we want to understand, right? So how these things decay through time, how much is left, we can apply this then to things like processes of interest with the radionuclides that we want to use. And I'm going to talk about 4 different radionuclides, fairly short-lived, it's all relative, but the 4 nuclides I'm going to talk about are cesium-137. This is man-made, introduced into the environment through testing of nuclear weapons. Cesium-137 has a half-life of 30.1 years, ultimately gives 2 geochrono horizons, right? 1953 and 1963. I'll come back to that in a little bit. Lead-210 with a half-life of 22.3 years, ultimately can be used for the last 100 to 120 years, looking at sediment deposition, sediment accumulation across a lot of different environments. And then there's shorter-lived radionuclides that I use a lot for looking at short-term sediment dynamics, whether that's mixing or rapid deposition, are beryllium-7 with a half-life of 53 days, and in the marine environment, thorium-234 with a half-life of roughly 24 days. I'll try to cover different aspects of these throughout this presentation. I'm going to start with trying to understand the laboratory technique a little bit more and how these are analyzed. We use 2 different processes, primarily for lead-210. All of these radionuclides can be measured by gamma spectrometry. And gamma spectrometry has an advantage in that all you need to do is take these samples, grind them up to a homogeneous powder, pack them in whatever standard geometry that you use for your detector, how your detector is calibrated, and count it. And so this particular counting of laboratory approach is non-destructive. You can use these samples again after you have counted them on your gamma detector. It's fairly simple. You dry, you grind to homogeneous, and then you pack it into a standard geometry that you use for your detector. And then you can analyze all of those nuclides of interest. In one sample, you can analyze thorium-234, beryllium-7, cesium-137, and lead-210, both total lead-210 and supported lead-210. That'll be important here in a few minutes. However, when thinking about gamma spectrometry, there are some cons, right? There's some negative to it. It's fairly low sensitivity. high background, not great efficiency, depending on which energy you're looking at. And so it's got fairly low sensitivity. You do have to correct for self-absorption, particularly in those low energies. Thorium-234, lead-210 in particular, you must correct for self-absorption. What that means is when a gamma is released through the decay of, say, lead-210, that gamma might actually be absorbed by the sample itself. And so the gamma actually never makes it to the detector to be counted. You can correct for that. It's another step. You have to correct for self-absorption, particularly when analyzing for those low energy lead-210, thorium-234. And you have to have a good efficiency calibration. So you need to have several different standards for the radionuclides that you are interested in measuring, because you need to have an efficiency at the peak of interest. So for thorium-234 at 63 keV, for lead-210 at 46 keV, for cesium-137 at 661 keV. You need to have the efficiency at those different energies of interest. And so the calibration isn't as simple. And if you change geometries, that changes the efficiency. Those are things you have to take into account. Again, you can measure all of these at the same time, so that's important to recognize. Alpha spectrometry can be used for lead-210. The advantage there is faster throughput potentially and much higher sensitivity. Analyzing by alpha spectrometry, you have a fairly low background, high efficiency detector, and so your sensitivity, it goes way up. You don't need that much sample. Depending on your detector, for gamma spectrometry, you might be using 4 or 5, maybe as much as 10 to 15 grams dry of material. For alpha spectrometry, you're only using maybe as little as a half a gram dry, maybe 1 to 1.5 grams dry. And so there's a very large difference in how much material you need between these two different approaches. Again, alpha spectrometry for the 4 radionuclides that I'm talking about will only work for lead-210. Detectors are not as costly as those for gamma spectrometry, and they're easier to maintain. For gamma spectrometry, you have to keep these detectors cold at liquid nitrogen temperatures. For alpha spectrometry, very little maintenance on the detectors themselves. Because it's high efficiency, because you tend to have many more detectors. So for instance, I have 4 gamma spectrometers, I have 16 alpha spectrometers. And so my sample throughput for alpha spectrometry is much higher. I only count for a day or 2. I can count as many as 16 samples at a time. So my sample throughput is much faster, and the efficiency is better. However, in order to analyze for alpha spectrometry, you're actually analyzing the granddaughter of lead-210, not lead-210 itself. So it's assuming secular equilibrium, that the activity of polonium-210 is the exact same of lead-210, typically a very good assumption. It requires a fairly time-consuming chemical separation. You've got to clean these samples up through a geochemical separation, typically a digestion procedure. I can usually run through about 40 samples in about 2 days in my lab. But again, that takes 2 days to prep these samples, 40 samples, to get them ready for counting. And it is a destructive process. You cannot reuse those samples once you move through that digestive process. So again, you sort of positive and negatives to both of these. In my lab, I typically run my samples by gamma spectrometry to start, primarily to get that cesium-137 peak, or if I'm interested in the short-lived radionuclides. And then after that, I will run all of that core for an individual core. I will run them all by alpha spectrometry to get that better throughput, to get the better analysis for the lead-210. When looking at geochronology for lead-210 perspective, lead-210 is good for about 100 to 120 years before present. The principles behind it are a product that lead-210 is being produced through the decay of radon-222, which is a short-lived inert gas that is produced through the decay of radium-226. And radium-226 is pretty ubiquitous across this planet. And so you're constantly generating radon-222. That radon-222 in the atmosphere decays fairly quick with a 3.8-day half-life to generate lead-210, particle reactive. Lead-210, therefore, is constantly falling out of the atmosphere, both dry and wet fallout. Now, it will vary some depending on where you are across this planet, but ultimately what we've seen, certainly over these sort of decadal timescales over the last century, is lead-210, how it's falling out is fairly constant at any one region across the planet. And so you can use that constant fallout of lead-210 to then use it as a chronometer in different environments, both terrestrial, on land, wetlands, or marine lacustrine. So thinking about lead-210 chronology, it's important to understand some of the principles behind it, the idea that we have supported lead-210 versus unsupported, or sometimes referred to as excess lead-210. And this is an ideal curve shown in the upper right, where the y-axis going down is depth or time, and then the x-axis here at the top would be the activity of lead-210. And going down core, what you'll find is that there is some supported lead-210 found within the grains of material, right? Whether it's sediments in a marine environment or the soils that you might find in a wetland. Within the mineralogy, within the minerals of those sediments, you have radium-226, that direct parent, within that matrix. And so you have already lead-210 being supported by radium-226 in secular equilibrium, same activity within those sediments. But as those sediments were making its way to whatever environment, again, a continental shelf, an estuary, a wetland, as it was making its way to its final resting place, it was picking up lead-210, whether it was from the atmosphere or maybe it was through water column scavenging. It was picking up excess lead-210 and its transport to its ultimately resting place in that core that you have collected. And it's that excess lead-210, that unsupported lead-210, that is decaying through time, right? And that time is set at a half-life of 22.3 years, right? A known constant. And it's that time that we can use to understand how sediments are being laid down and the time scale at which sediments are being accumulated at that particular environment. And we can use that then to calculate this S, which is the sediment accumulation rate, based on how the initial activity is changing with depth in that core. Here, Z is depth, lambda is the decay constant for lead-210, right? It takes into account the half-life, so it is a constant. Now, it's important to recognize that this curve can be generated in other ways other than just decay of lead-210, right? Through that process of decay. Mixing of sediments, whether bioturbation or physical mixing due to waves, can create a similar curve. And so you need to understand your environment. You need to be able to state whether mixing is important or not before you model these sediments with the assumption that only accumulation is what's important in that particular core, because mixing can play a role in creating a curve like this for lead-210 or other radionuclides. So when thinking about lead-210 models, there are many assumptions and there are many models that you can use. I put the three most common models that have been used in a lot of my papers and a lot of other papers, and how it's applied both in marine, wetland, and lake environments. Those three are the constant flux, constant supply. So this first one, also referred to as the simple model, the constant rate of supply, and the constant initial concentration. So three different primary models that are used. There are other Bayesian type models that have been applied more recently. The assumptions are sort of stated up here and referred to in this table down here. So specific activity, whether it's constant or variable, the accumulation rate through time, is it constant or variable? That flux of lead-210 in the environment, is it constant or variable, right? So ultimately, that's what this is summarizing and up above in this one table. I show this for lead-210, but you can apply this on very much shorter time scales talking about weeks to maybe a few months using beryllium-7 and thorium-234. And so if you have an environment that has rapid sediment deposition, you can actually use thorium-234 in a marine environment or beryllium-7 in a fresh or marine environment to understand rapid deposition, in the same approach that I'm showing here for lead-210, using those same mathematical equations as well. But it's important to recognize, particularly when using lead-210, that mixing can play a role, right? So this assumption, one of the main assumptions, is that mixing is negligible to apply these models. Well, it's important when using lead-210 to have an independent chronometer, and often cesium-137 is used. Plutonium-239, 240 can also be used, almost identical, although the application and the laboratory techniques for using plutonium-239, 240 is a little bit more time intensive and difficult, but can be measured through alpha spectrometry like I've shown you for lead-210. But let's just focus on cesium-137, its depositional history. Again, cesium was introduced into the atmosphere through the testing of nuclear weapons. That testing took place in the atmosphere, in the ground, in the ocean, and basically dispersed cesium-137 throughout the atmosphere, although different for the northern versus southern hemisphere, given that most of these nuclear explosions, particularly in the atmosphere, were done in the northern hemisphere. So you can see that deposition history and the darker colors in the northern hemisphere much higher than in the southern hemisphere. And please remember that we are now beyond two half-lives for cesium-137 when it was initially introduced. And so the activities for cesium in many of the environments that we're measuring have declined significantly. However, there are two chronohorizons that we typically use for cesium: when it's first present in a core, which represents roughly 1953, and then the peak of cesium, which is 1963. There are some regions that might have another peak in the 80s and 90s associated with accidents that have taken place. So you need to take that into account for your region where you might be collecting a core, if there are any other potential sources of cesium post 1963 peak associated with atmospheric testing. So you can use cesium in combination with lead-210 to get very good results for decadal scale accumulation rates and geochronometry of cores from many different regions. And so as an example and I just want to show a couple examples of where I've done some work across the globe. This is a mangrove environment, a wetland environment, continental shelf environment, estuarine environment. So I've done work around the world in a lot of different environments, applying these 4 radionuclides for looking at sediment dynamics on very different timescales. More recently, a lot of my work has focused on sea level applications in partnership with a lot of very smart scientists. And my contribution has been developing some of the geochronometry for the last 120 years using lead-210 and cesium-137. And this is one example, the reference down here at the bottom, one example of basically applying a lot of different chronometers, not just lead-210 and cesium-137, but several different chronometers to get a high resolution depth age model, such that you can then use other results that provide some understanding of sea level with time, that allows you to develop a relative sea level reconstruction, right? The curve that has been reconstructed, shown down here, relative sea level through time. This is for an area, multiple curves in New England in the US. This is one application where you can use different types of chronometers. And again, lead-210, cesium-137 being applied here in many of the studies that we've worked on for developing these sea level curves through time in different locations around the world. I want to show a couple examples, both for the short-lived radionuclides, thorium and beryllium, as well as lead-210, and how we've applied those This is showing the Mississippi Delta. So this is coastal Louisiana, the continental shelf off of the Mississippi Delta. And I'm going to show a couple cores that we've collected in some studies that we've done sort of just west of the Mississippi Delta. The first is using these short-lived radionuclides that I talked about initially, right? So beryllium-7, thorium-234. You can apply these if you actually go out to a study area and collect cores every couple weeks or every month and a half or so. You can actually use these radioisotopes to understand deposition and erosion, not just the deposition of sediments, but you can look at these dynamics in a system, deposition and erosion. And the way that works is by going out, collecting that initial core, and analyzing these short-lived radioisotopes for beryllium-7 and thorium, and seeing what you have. Maybe you have no activity at all, or maybe you have some activity of that beryllium or thorium. Going out a couple weeks, a month later, collecting a core in the same location, and then seeing how that core has changed, seeing how that down core beryllium-7, thorium-234 has changed. If you integrate that, right, you get the inventory of beryllium-7 and thorium for that location, you can then start seeing how it changes through time. And so going from that initial core to a subsequent core, what do you see? Do you see new activity, a new inventory of beryllium or thorium, or maybe no change? If you had some beryllium or thorium present in that initial core, you can then decay correct that to see what you have in the subsequent core. Do you have new material in addition to what might be left over that had decayed through time, shown here? Versus maybe you just had erosion that took place or no change. The inventory that you see in that subsequent core is based on what you would see solely on the decay of what was present there. And we've done that across the continental shelf off of Louisiana, taking cores in a proximal, an intermediate distant, and a distal distance from that major river source, the Mississippi River, to understand those short dynamics of sediments related to the river and how the river was flowing versus the energy in the environment, the waves and currents in the environment, to really look at whether material was depositing or potentially eroding on these different timescales. And it's these short-lived radioisotopes on timescales of weeks to months that can really give you new insight into how sediments on a continental shelf or other environments are changing with time. Another example, and this might be my last example, storm-related. Had we not had measurements of these short-lived beryllium-7, thorium, as well as long-lived lead-210, we might not have been able to tell the full story of what was going on in the continental shelf post hurricanes in this location. So this is actually a core we collected back in 2005 after that particular area had been hit by several storms over a couple of different years. So 2004, Katrina and Reide, those storms occurred in 2005, and we actually collected this core about 10 days after Hurricane Reide came ashore. This is an X-ray for that same core. You can see down deep in the core below about 38 centimeters, you can actually see some bioturbation, and you see this really nice laminations and some distinct areas in the core. And what we were able to actually do is define what these different stratigraphic horizons represented based on the radiochemistry. So based on the fact that we have thorium-234 and beryllium-7 present in these upper two layers, not present in this deeper layer, but the lead-210 gives us some indication of what was happening within all three of these layers with time. And in fact, really interesting story that we have some of that published here, does get into how these storms pulse across the shelf, sending sediments from shallower waters into deeper waters. This was collected in about 80 meters of water. But it's those short-lived radionuclides that really helped us provide the story, a better understanding of how sediments were being transported across the shelf and the timing of that using the combination of lead-210 with beryllium-7 and thorium-234. Going back really quick to this original image that I showed, the fact that we can use these short-lived radioisotopes, thorium, beryllium, in combination with some longer-lived, granted, it's all relative. What I'm really focused on in this particular presentations are short-lived, but these short-lived for us were anywhere from 22 years to 24 days, so quite the span there. But you can use these in combination to understand dynamics of sediments, sediment accumulation, and in combination with longer lived, like C14, looking at sea level curves and the restructuring or reconstruction of sea level curves for some areas. And we've applied these particular radionuclides across many different environments in wetlands, mangroves, nearshore, estuaries, lakes. The key is understanding something about the environment. Are you looking at primarily dynamics associated with mixing? Are you looking at sediment accumulation on timescales of decades, or maybe rapid deposition that requires a very short-lived radionuclide in order to understand those sediment processes? I appreciate the time. I realize that was quick. I look forward to any questions that you might have, but I hope this gave you some insight into the application and maybe some of what it takes in the lab to do some of these analysis in order to get the information from these radionuclides. Thank you very much, and look forward to some of the questions you might have a little later.